Dear viewers, in this video we will learn about the flow of classification of random hardware faults used in the FMEDA calculation with some examples. This is covered in the Annex B of ISO 26262 Part 5. Let's begin. There are some prerequisites before we start our FMEDA analysis. Failure mode analysis for each hardware component from the BOM is ready. Hardware effect for each failure mode is assessed. Fit rate for each hardware component is performed using reliability analysis. Failure mode distribution is also available. Let us take a simple driver notification system for our analysis. This has a micro, a transistor, and an LED and a buzzer. The LED is driven from the micro using a transistor, which is a switch, and we have a safety goal related to the LED. This LED is used to indicate a malfunction of the safety feature. We also have a buzzer which is not safety relevant for our concept. We'll take switch as the hardware element for our analysis. This has two failure modes, open circuit and short circuit. The hardware effect: when there is an open circuit, the indicator will not follow its input. It will always be turned off, which is a violation of safety goal. When there is a short circuit, indicator still not follows the input, but it is always turned on. For us, it's a safe fault. Each hardware element and its failure mode will be considered for the FMEDA analysis. First question is the hardware element and its failure mode is safety related? In our example, if we look at, we saw three elements: transistor, LED, and buzzer. Now we are going to ask this question on these three elements. Is it safety related? Switch and LED are safety related as they are part of the safety functionality. Failure of these two is going to violate the safety goal. Buzzer is not safety related as it is not part of functional safety. Coming back to the question, safety related is no for the buzzer, so its failure modes are not included for the FMEDA analysis. Safety related is yes for LED and switch. Next question is potential to violate safety goal. Let us take switch here. The open circuit of the switch is going to violate the safety goal as we saw in the first slide, and short circuit is a safe fault. Coming back to the question, potential to violate the safety goal: yes for open circuit and no for short circuit. For the failure mode, which is going to violate the safety goal, do we have a safety mechanism in place to address the failure mode? No, because currently we don't have any safety mechanism in our architecture. So all those failure modes will be treated as single point faults. Let us consider we added a safety mechanism to monitor the correctness of the LED using ADC. And coming back to the question, do we have a safety mechanism in place to address the failure mode? Yes, and we have safety mechanism, telltale monitoring using ADC. Now next, we need to see the diagnostic coverage of the safety mechanism. How much is the failure mode the safety mechanism is going to cover and how much is not. So the failure mode that is not covered by the safety mechanism becomes residual fault. Now single point fault and residual fault, both together called as single point fault, and it is provided as order of 1, which means single independent fault led to a safety goal violation, and we have safety mechanism or not, both together called as single point fault. Now we completed the single point fault analysis, which means single independent fault leading to safety goal violations are analyzed, safety mechanisms are added appropriately, and the failure which is related to residual faults and single point faults are improved. Next, there could be chance that single independent fault might not violate the safety goal, but it can still violate the safety goal when it combines with one another fault. That can occur in two ways. One is two independent fault in the functions can lead to a safety goal violation. In our example, Let us see two independent switches are driving the same tilt redundantly. Failure of any one switch is not going to violate the safety goal, which means the other switch is still going to drive the LED. What if both the switches are failed at the same time? This is called two independent failure in the function. Second way is function and safety mechanism failed at the same time. For example, the switch which drives the LED is failed. To detect the LED status, we add the safety mechanism using ADC. The switch is failed and the ADC peripheral as well failed. These two can lead to the safety goal violation. Again, the same question, whether we have a safety mechanism in place to address this fault, or can the driver perceive the effect? Here we see one additional terminology used. Can the driver perceive the effect? If we look back in the definitions, perceived fault, so the driver can perceive the effect at vehicle indirectly. For example, let us take headlamp is not working at night. Can the driver perceive this or not? Headlamp is not working, plus the safety mechanism added for the headlamp failure detection is also not working, which is a two independent fault occurred at the same time, and still the effect of the failure can be perceived by the driver. Similarly, wipers are not working. Complete displays of those are all can be perceived by the driver. Let us take tail lamp is not working. This cannot be perceivable by the driver. Safety mechanism is in place to address this failure mode, or can the driver perceive the effect of this failure mode? If both are no, then the hardware element's fault is called as multi-point fault latent. Now we added a safety mechanism to detect the failure of the ADC peripheral, ADC self-test. Coming back to the question, safety mechanism is in place to address the failure mode? Yes, using self-test of ADC. The safety mechanisms which is not going to cover the failure is still called as multi-point fault latent, or the effect of the failure mode is not perceivable by the driver is also called as multi-point fault latent. On the other side, the safety mechanism which is covering the failure is called as multi-point fault detected fault, and the effect which are perceivable by the driver is also called as multi-point fault perceived, both together called as multi-point fault detected or perceived fault. Multi-point fault latent is also called as latent point fault, and the order is equal to 2. As we saw, single independent fault violated the safety goal called a single point fault. Single independent fault is not violating the safety goal, but it is still going to violate the safety goal if it combines with one another fault, which means two independent fault occurring at the same time leading to a safety goal violation. It is called latent point fault. It is also called as dual point faults. We analyzed the single independent fault and its safety goal violation, and then we analyzed two independent faults occurring at the same time and their safety goal violations. And now it talks about more than two faults. According to ISO 26262, n greater than 2, which means more than two fault occurring at the same time is treated as safe fault unless it is safety relevant as per the concept. Single point fault, residual fault, multi-point fault latent, multi-point fault detected or perceived, safe fault. These are all the fault terminologies used in the FMEDA. Single point fault and residual fault together called as single point fault. Multi-point fault latent is called as latent point fault, also called as dual point fault. Hope the video provide information about different faults used in the FMEDA analysis. Stay tuned. Contact us at autofunctionalsafety@gmail.com if you have any questions on this topic. Thank you for watching.